This is Euclid Book 10, proposition number 42, and this is the diagram right up here. And it says, a binomial straight line is divided into its terms at one point only. Let AB be a binomial straight line divided into its terms at C. Okay, so we got AB, which is the straight line, and it's divided into its terms at C. Okay. Therefore, AC and CB, well, this is line AC right here, this is line CB right there. These lines are rational, and they are commensurable in square only. And I've taught you that many times. Now we're going to go by hypothesis and say, I say that AB is not divided at another point into two rational straight lines commensurable in square only. For if it were possible, let it be divided at D. So now we're going to have this little letter D right there. Also, so that AD and DB, so now we're going to have AD and DB, okay, AD and DB, we're going to have that, are also rational straight lines commensurable in square only. And you now know what that means. It is then manifest that AC is not the same with DB. So now we're going to say that AC and DB are not the same lines. For if possible, we're going to assume that they are. Then AD will also be the same as CB. AD would be the same as CB. And as AC is to CB, now we're going to be setting up a ratio. As the length of AC is to the length of CB, so will BD be to DA. So will BD to DA. Thus, AB will be divided at D also in the same way as by the division at C, which of course is contrary to the hypothesis. Therefore, AC is not the same with DB. AC is not the same with DB. For this reason also the points C and D are not equidistant from the point of bisection. Therefore, that by which the squares on AC and CB, now at this point we have to stop. Alright, you're going to make a square. All four sides of that square are going to be the length of AC. Make the square. When you're done, then I want you to make another square. And all four sides of that square are going to be the length of CB right there. And then it says, therefore, that by which the squares on ACCB differ from the squares on ADDB. Okay, so that means we're going to have to draw two more squares. The first square is going to have all four sides the length of AD. So, see, there's the length of AD. We're going to make all four sides of that square that length. Okay. Now we're going to draw another square. And all four sides of that square are going to be the length of DB. Now, do you have all four of those squares drawn? Okay. Therefore, that by which the squares on ACCB differ from the squares on ADDB is also that by which twice the rectangle ADDB. Okay. Now we're going to have to draw a rectangle. Two sides of that rectangle are going to be the length of AD right here. The other two sides of that rectangle are going to be the length of DB. Okay. So we got a rectangle. Two sides are AD, two sides are DB. Okay. Now then. Let's go back through this. This is just one little paragraph, but we have to go through this several times. We're going to have to draw a lot of stuff. Therefore, that by which the squares on ACCB differ from the squares on ADDB is also that by which twice the rectangle ADDB, which we just drew, differs from twice the rectangle ACCB. Now, what is rectangle ACCB? Okay, we're going to draw a rectangle. Two sides are going to be the length of AC. Two sides of that rectangle are going to be the length of AC. The other two sides are going to be the length of CB. Okay? You got that rectangle drawn? Very good. So, the squares on AC and CB, if added together, all that area added together, is different from the squares on AD and DB. So you take the area of AD and the area of DB and you add that together. And those two areas are not the same. It is also true that if you take the area of the rectangle ADDB, you multiply that by 2, that area is going to be different from the other rectangle you drew, which was ACCB, and you multiplied its area by 2 as well. And why is this true? Because both the squares on ACCB, together with twice the rectangle ACCB, okay, so now we're going to take the squares on AC and CB, we're going to add their areas together, and then we're going to add twice the area of rectangle ACCB. And the squares on ADDB, if we add those together with twice the rectangle ADDB, okay, we got all this area all added together. That whole bunch of areas all together is equal to the square on AB, and this is by Euclid Book 2, proposition number 4. But the squares on ACCB differ from the area, but the squares on ACCB differ from the squares on ADDB by a rational area, for both are rational. Therefore, twice the rectangle ADDB also differs from twice the rectangle ACCB by a rational area, though they are medial, which is by Euclid Book 10, proposition number 21, which is absurd, for a medial area does not exceed a medial by a rational area. This is by Euclid Book 10, proposition number 26. Therefore, a binomial straight line is not divided at different points. Therefore, it is divided at one point only. And that is the whole proof. I will tell you more in my next video, so I want you to stay tuned.